Hello students, let's continue our lecture. Today we are going to discuss about Francis turbine and Kaplan turbine. As you have already discussed, this Francis turbine and Kaplan turbines are the reaction type turbine. Okay, strictly speaking, Kaplan is purely reaction type turbine. However, Francis is partially impulse, partially reaction type turbine, because it is said that when water flows, by the way, this is the image of a runner. Okay, Francis turbine's runner, and this is one particular blade. If you take it out, and this the one particular blade would look something like this, and this whole thing is inside this spiral casing. Okay, and this is this shaft. When water enters this in the radial direction and it exits actually, okay, that's why it is also known as mixed flow type turbine. So water gets into here, and this spiral, as you have noticed, the diameter of a spiral goes on decreasing. That is because as water flows from here, the water that is coming from here already gets into the turbine and it gets out, so that the quantity of water here and here is not same. So to adjust that, the size of the spiral casing goes on decreasing. Okay, so everything is housed inside this spiral case, and this is where water is discharged to the tail race, and this portion is known as draft tube. We will discuss about draft tube in later videos, but right now let's understand that Francis is uh, it is a mixed, as we have already said, it's a mixed flow type turbine. It's a reaction, and strictly speaking, it is not just reaction, but some portion there is an impulsive force. When water moves from here, it also exerts impulsive force on the vane. Okay, that is what you need to understand from this slide. Moving on, you see, I have brought you here a small animation. See, this is the runner. Okay, in previous slide, what I have shown you is the, in fact, the isometric view, right? It is somehow not exactly isometric, but it is in a three-dimensional view, so you can make a sense. Now, if you see this, you keep this perfectly horizontal and you see from top, that's what you're going to see here. So this is the main runner, and the runner is, there is a guide vane. This guide vane actually controls the water quantity that flows into the turbine or the runner. It controls it is adjustable. Okay, these vanes are adjustable, and then there are other stay vanes. This stay vane, the main purpose of this stay vane, which are located in the outer periphery, it's direct the flow into the runner. Okay, it is, this angle is so adjusted that at what angle would give the maximum efficiency, so that angle is, that will direct the flow in that particular angle. And these guide vanes, stay vanes, guide vanes, these guide vanes will control the quantity of water that flows into the turbine. Now, if you consider this as a one particle, water particle, just observe the animation. Okay, how it goes. So exactly this is how water moves into the turbine. If you're not able to catch this, I'm again, once again playing this. You can have a look. You can just observe the pink dot, which is a water particle. So this is how water moves. Okay, and this is the motion, the path of the water that takes. So it is guiding the, this stay vane is guiding the water. This controls the volume, and then it goes into the runner, and this is the blade of the turbine. And here, this is a guide vane. In three dimensional, it will look like this. A top view is, this is how a top view would look like. And inside this, there is the runner, and outside this, there is the stay vane. Okay, now just see how this controls the volume. This is the maximum opening, and this now it's closed. Once again, this is the maximum opening, and this is how it closes. When it closes, there is no water flowing, and maximum opening, there will be maximum water is let to flow into the runner. Okay, with this much of understanding, let's try to understand the work done by the turbine, or by the water, by the turbine. Okay, so as we have already discussed, we always have to start with the construction of a velocity triangle, and this is the typical velocity triangle for Francis turbine. Okay, and the side view of a Francis turbine looks something like this. Okay, and the top view, this is the top view, this is the runner, this is where the water exits, and there are some guide vanes outside this, and after this guide vanes there are the stay vanes. Okay, now we are just talking about one particular vane, this the runner plates of the runner. So this is the inlet triangle, this is the exit triangle, and from this two triangle we can calculate the force and then the work done. Like usual, force is equal to change in momentum, that is momentum flux going out of the system minus momentum flux coming into the system in particular direction. Here direction T means we are considering the tangential direction. Okay, that's tangential direction. T stands for tangential direction. So minus f of t, because like always I always put a force in this direction to calculate the force, right? So minus, because it's going in minus direction, so minus f of ft. Okay, not f of t or ft, anyways, you understood, right? This is f, this is the force along the tangential direction. Okay, now the momentum that is going out, the momentum that is going out is mass times velocity. Mass is rho q, velocity is w2, vw2. Vw2 is the wheel velocity that is going out, that is in positive direction. See, it will have a radial component, it will have a the tangential component, right? So this tangential component of absolute velocity is also known as the wheel velocity, and that is what we have to take into consideration. Now it is in positive direction, so it is positive. Minus is coming from minus, again w2, again, oh sorry, w1 is in positive direction. Okay, that is going, just hold on a second, I'm in second line. Okay, so minus f of t, because minus in opposite direction, w rho q w rho q vw2. So like I have explained, minus is this minus rho q w1, there's a momentum, influx momentum. So rho q is the mass flow rate times vw1. Vw1 is also in positive direction, that's why it is minus here. Now you multiply by minus 1 throughout, you get f of t is equal to rho q vw1. This becomes positive and this becomes negative, so that's how we got it. So next is the work done. Work done, you know, it is force times the velocity. So if you multiply here, but see, this is exit, right? This is, sorry, this is the inlet and this is the exit. So to when you multiply the velocity, you have to multiply the inlet and the outlet respectively. Okay, so when you multiply it, you will get this expression. So this is the work done for Francis turbine. Now see, observe carefully. Work done will be maximum when VW2 cannot be zero because it is moving, right? VW2 can be zero if the velocity, that is outgoing velocity is a radial direction. If it is a radial direction, then VW2 will have no component in tangential direction. So work done will be maximum, VW2 will be when VW2 is zero. So this condition is achieved when the outgoing velocity is in the radial direction. So let's assume if the velocity was going in radial direction, so the maximum work done will be rho q vw1 u1. I believe this is the equation that has been derived in your textbook, but also you need to notice that it is only applicable when v2 is in radial direction. In question, if it says if it is not in radial direction, in that case you have to use this equation. Okay, so you have to read the question thoroughly, and you also have to understand how these velocity triangles have been constructed. So with this much of knowledge, then you are good to go. And again, the hydraulic efficiency is given by power developed by power supplied. Power developed is work done per second. So in fact, I have written work done, but this is work done per second because it is mass flow rate. You know this, right? We have been discussing this. So divided by power supplied is rho qgh, right? This h is the total head. So then we get g only rho q will go off, and this parameter minus gh will remain. Again, the mechanical efficiency is given by power available at the shaft divided by power developed. Now this is the power developed, and power available means whatever the power it was available on the shaft. So once your turbine starts to run, and then you measure how much power it has actually developed, so that is the power actually available at the shaft, that would be the power here. Okay, and the overall efficiency is given by the mechanical efficiency times the hydraulic efficiency. Okay, And unlike the impulse turbine, we don't have volumetric efficiency because all the water would definitely at some point of time it will come into interaction with these vanes. So the volumetric efficiency, if there, it can consider to be 100%, or else it is very less that it is ignored here. Okay, with this, let's continue. And again, this is a case where in your textbook it has described. Okay, so this is a particular case when discharge is radial. Everything remains same. So understand, this is the outlet velocity, this is the inlet velocity. I've already explained the work done will be maximum when the V2 is put 90 degree with U2. So that is the condition I have again derived. In fact, it was already discussed in previous slide, but in your textbook it is derived in this fashion. So I thought it would be good for you to not to get confused. Okay, so everything remains same. Work done will be VW1 U1 because U2 is becoming 0. And again, you substitute the same thing in the equations, you will get the respective efficiencies and overall efficiencies, the multiplication of hydraulic efficiency times the mechanical efficiency. One more term comes, that is the degree of reaction, and the degree of reaction is described as it is the ratio of pressure drop between inlet and outlet to the work done per unit weight of water. So this expression gives you the degree of reaction. Okay, with this, let's try to solve a numerical then. So the problem says a reaction turbine, not particularly saying Kaplan or Francis, but reaction, which means it is applicable for both. Okay, so it is not especially it is not describing the Francis turbine. So the analysis remains same for both the reactions turbine. Okay, the main maybe some formulas will change, but the analysis remains same. Okay, let's read this question. A reaction turbine works at 450 rpm under a head of 115 meter. Its diameter at inlet is 1.2 meter and the flow area is 0.4 meter square. The angle made by absolute and relative velocities at inlet are 20 and 60 degrees respectively with the tangential velocity. Determine the discharge through the turbine and power developed efficiency. And see, it is assumed the radial discharge, the discharge is radial at outlet. So what does that mean? It means V2 has no wheeling component at outlet, which means the work done is given by, we don't have to substitute, we don't have to put that minus VW2U2. Okay, so that is the work done. All right. So like always, I have drawn the inlet velocity triangle, outlet velocity triangle. So here V2 is 90 degree with U2, and this is our usual notation. We put it alpha, that is 20 degree. This usual notation, we put theta, that is 60 degree, and U1 can be calculated because the diameter is also given and also the speed is given. So using this, we can calculate U1. So this value we have calculated. Now further we can calculate V1, that is absolute velocity at inlet. So now we know this angle, we know this angle, we know this length, we know we need to calculate V1. We can apply the sine rule. Then sine rule says the length divided by sine of the opposite angle equals to the other length and the divided by a sine of other angle. So here V1 divided by this angle should be equal to U1 divided by this angle, and you know this is 60 degree, this is 120 degree. So here it should be 120 degree, but we know from the property of sine theta that sine theta equals sine 180 minus theta. So sine theta, sine 60 or sine 120 is one and the same thing. So I just put 60 here. So from here we calculate V1. Likewise, we can calculate power. So you substitute everything except for Q is not known. So we can calculate Q. Area is given. Now Q is area times velocity. So we have so many velocities here. Which velocities to take here? Which velocity do we need to take? So here by the name only we can make a guess. The VF is known as flow velocity. It is said that the wheel velocity, WHIRL, the wheeling velocity is the velocity component that is responsible for the turbine to make it rotate, okay, to rotate it. The VF, the flow velocity, is responsible for flowing water in this direction. So we always have to use the flow velocity component to calculate discharge. Please keep this in mind, okay? And likewise, we substitute the value of Q and everything, rho is known, and the rest we substitute in this, and then we calculate the power. And hydraulic efficiency is power developed by power supplied. Power developed we have just calculated, and power developed we have calculated it, and we can now substitute, we can now calculate the power supplied, that is rho QGH, and then we can find the value for hydraulic efficiency. That's it. Okay, now let's discuss on Kaplan turbine. Like I said in previously, Kaplan turbine is a pure reaction turbine, which means the work is done because there is a pressure gradient at inlet and outlet. So this is the casing, okay? The casing, the spiral casing, one side will be bigger than the other side, and from the casing, water gets into the turbine, right? So here is the runner, this is the hub, this is the Kaplan turbine. So when there's a pressure difference, when water flows, there's a reaction force acting on the vanes that would make this rotate. That's the principle of Kaplan turbine. And this guide vanes looks something like this. I have already shown you in the previous slide. So this is how it looks, okay? The guide vane. So this controls how much water it gets into the turbine. And the tube that connects the turbine outlet to the tail race is known as draft tube. So here it is the conical draft tube. Okay, so this is the layout of a turbine. This is the X section, in fact, X section of a Kaplan turbine. You may need to understand how to draw this because it can be asked in examinations. Okay, further, let's understand the velocity triangles of a Kaplan. So if I just take out the Kaplan turbine, this is how it looks from the side view, and this is what it looks from the top view. Notice that these vanes are adjustable, which means right now it is in this angle, right? It can be adjusted, right? If it cannot be adjusted, then it is known as a propeller. And if in the Kaplan turbine, this plates or the vane, as you call, it can be rotated about the center point. Okay, so from the top view, it looks something like this. So water is coming in contact with the vanes in this fashion. Okay, so it enters from this point and exits from this point. Now what you need to understand is these locations are at the same distance from the center of the turbine. That's why the tangential velocity at inlet, that is at this point, and the outlet is same. So this is what is different from the Kaplan, from the Francis turbine. Inlet velocity, inlet tangential velocity, and outlet tangential velocity at inlet and outlet is same, because see, these 2 points are located at, I mean, more or less in the same radius from the center. That's why it's u1 and u2 is equal to u. Okay, and this is the velocity triangle. So if you make a section here, this is how it looks, and this is the velocity triangle. Okay, and here I have written VF2 and VF1. This is the flow velocity, indicating that the work done will be maximum when the absolute velocity is in a radial direction. If this is the condition, then there will be maximum work done. That's why it is in textbook also, they have also referred the in textbook also they have made the diagram in the same fashion. Okay, so this is the meaning. And work done and the analysis remains same, just that the difference is u1 and u2 remains in Kaplan turbine. U1 and u2 is equal, and VF1 and VF2 are also equal in Kaplan turbine. The discharge formula, however, is different, because you see the layout of a turbine is different, right? So see here, so this is the total diameter, and there is the hub, or this portion. Okay, so to calculate the portion from where discharge actual flow can occur, this is the discharge. And since this is a circular, So we have to find the area of total diameter minus we have to find the diameter of this, and we need to subtract. That's the only difference. So if you take this, this is the outer diameter, exterior diameter, and this is the interior diameter. Exterior diameter means from this point to this point. Interior diameter means I am taking from this point to this point. So when you subtract this areas, then you get the flow area multiplied by the velocity of flow. That will give you the discharge. Rest, I mean, more or less everything is same. And also the solving techniques, problem solving techniques are same with that of the Francis turbine. Okay, so with this I would like to stop this lecture here, and we'll continue with draft tube theory and surge tank and other topics of this chapter. Thank you.